We have events A, B, and C, and then we're given the probabilities and the combinations as a Venn diagram. And the first question, 10.1.1a, says that let's find y, the probability that none of the events will occur. The probability that none of the events will occur. So the probability that none of the events will occur is always equals to 1 minus the probability that at least one of the events occur. And then that is given to us on the question statement. It is said that the probability that at least one of the events will occur is 0.893. So the probability of y is just 1 minus 0.893, and that is 0.107. Now we can do B. B is saying that let's calculate the value of x, the probability that all the 3 events will occur. The probability that all the 3 events will occur. X is here. This is what we're looking for, the probability that all events will occur. We already know that the probability of at least one event occurring is 0.893. The probability that at least one event occurs is 0.893. So all these probabilities that we see here should be equals to 0.893, right? So if we do that, we're going to get 0.893 being equals to 0.05 plus 0.15 plus 0.05 plus again 0.1, 0.2, and 0.183 plus x, right? So now we're just solving for x, the probability that all 3 events occur. So 0.893 will be equals to, let me just add all these probabilities. I'm getting 0.733 plus x. So consequently, x should be equals to, so we're just saying 0.893 minus 0.733, which should be equals to 0.16. So now here at x, we know that we have 0.16, right? We have 0.16 at x. And then let's do 10.2. 10.1.2, I meant 10.1.2 is saying that let's determine the probability that at least 2 of the events will take place. The probability that at least 2 of the events will take place. So we need a formula for that. The probability that at least 2 events of A, B, and C occur. This will always be equals to the probability of A and B plus the probability of B and C plus the probability of C and A, right? Minus 2 the probability of A, B, C. Right, so we're gonna have the probability of A and B, so that will be 0.1 plus 0.16, right? So we have 0.1 plus 0.16 plus the probability of B and C. The probability of B and C will be 0.2 plus 0.16. So we have 0.2 plus 0.16 plus the probability of C and A, so that's 0.15 and 0.16, right? So we have 0.15 plus 0.16 and then minus 2 the probability of ABC, so that is minus 2 and then 0.16. You can see here that we counted 0.16 3 times and we're subtracting 0.1 twice, so that we end up counting it only once, right? So let me just put that in the calculator, and I'm getting 0.61. So the probability that at least 2 of these events will take place is 0.61. Let's do 10.1.3. So 10.1.3 is saying that are events B and C independent? Justify your answer. We have solved a very similar problem in the past, right? So what we have to do now, we have to stick to the definition. What does it mean when two events B and C are independent, right? By definition, two events B and C are independent if the probability of B and C is equals to the probability of B multiplied by the probability of C, right? So let's go ahead and look for the probability of B and C. So here on our Venn diagram, the probability of B and C is this 0.2 and X, which we know fully well that X is 0.16, right? So we have 0.16 plus 0.2. Being equals to, right? So we check in to see if they're equal to each other. So what is the probability of B? The probability of B is everything in the circle of B, right? Everything in here in the circle of B is the probability of B. So that will be 0.183 plus 0.1 plus 0.2 plus 0.16 multiplied by the probability of C. The probability of C will be 0.05. Everything in this circle here for C, right? Everything in this circle. 0.05 plus 0.15 plus 0.16 plus 0.2, right? So 0.16 plus 0.2, that will be 0.36, and it should be equals to that is 0.36008, and we can see that 0.36 is approximately 0.36008, right? So we can conclude and say that events B and C are independent of each other because they satisfy this definition here.
A 4-digit code is required to open a combination lock. The code must be even numbered and may not contain the digits 0 or 1. Digits may not be repeated. And then the first question, how many possible 4-digit combinations are there to open the lock? How many possible 4-digit combinations are there to open the lock? So let's look at the restrictions we have. We have digits from 2 to 9 because 0 and 1 cannot be used. So we have 2, 3, 4, 5, 6, 7, 8, 9. How many digits? This is 1, 2, 3, 4, 5, 6, 7, 8. The other condition that we have is that the code must be even numbered. What does that imply? If the last digit on the code is even, then the code itself is even numbered. So we need an even number to occupy the last spot. How many even numbers do we have? Well, 2 is even, 4 is even, 6 is even, and 8 is even. So we have 4 possible digits that can occupy the last spot. So we are choosing from 4. So out of the 8 digits that we have used 1 on the last spot. Now we are left with 7 and no further conditions. So we have 7 possible digits that can occupy the first spot. 6, 5. We have 840 possible 4-digit combinations. Let's look at 10.2.2. Calculate the probability that you will open the lock at the first attempt if it is given that the code is greater than 5,000 and the third digit is true. The code is greater than 5,000 and the third digit is true. Let's make sense of that. If the code is greater than 5,000, then on the first position, we need 5, 6, 7, 8, or 9. We need 1 between those 5 numbers. We say in only 5, 6, 7, 8, and 9 should occupy that first spot. Now let's look at the other condition that we have. We must have 2 on the third spot. So here we have only 1 digit that can occupy that spot. We have 2 there. And then on the last spot, for our combination to be even numbered, the last spot must be occupied by an even digit. We need 2 to be on the third spot, so we cannot include it anymore. So we are only left with 4, 6, 8. If you saw the last video I did on probability, you will realize that we have a conflict of interest now. 6 and 8 can occupy both the first and the last spot. So we need to make calculations for when 5, 7, and 9 occupies the first spot and when 6 and 8 occupy the first spot. So let's go ahead and do that. We only do that when we have a conflict of interest like we do right now. So let's have 1, 2, 3, 4. If 5, 7, and 9 occupy the first spot, then we are choosing one of the three. And then on the last spot, we are still going to have 3 digits. On the third spot, we have 1 digit that can occupy there, which is 2. And then on the second spot, of the 8 digits, we have used 1, 2, 3. So we are left with 5. This is when 5, 7, and 9 can possibly occupy the first spot. Let's look at the case when 6 and 8 occupy the first spot. When 6 and 8 occupy the first spot, we have 2 possible digits that can occupy the first spot. On the second spot, we're going to have 5 digits after we have satisfied everything else. On the third spot, we need 2, so that is 1 digit. If 6 or 8 occupies the first spot, then on the last spot, we are only going to be left with 2 even digits. Let's say 6 occupied the first spot, then we are left with 4 and 8. If 8 occupies the first spot, we are left with 4 and 6. So we have 2 possible digits that can occupy that last spot. Now it is just a matter of putting that in your calculator and you should get 65. So the probability will be equals to 65 divided by the sample space, our total possible combinations, which is 840, which will give you 0.08.